Hi everyone, my name is Muskaan, and my partner and I, Sahej, will be talking about our meta-analysis that we're currently working on regarding solute carrier or SLC transporters. So I'll give it off to Sahej to introduce himself and start off our presentation.
Hi, I'm Sahej, and I'm just going to start off with a brief introduction of SLC transporters. SLC transporters are transport proteins. They're one of the four types: ATP binding cassette transporters or ABC transporters, ATPases, ion channels, and solute carrier transporters, SLCs. And so the SLC transporters, um, there's over 450 of them. They're divided into 65 families, and they provide transport for a wide array of molecules like sugars, amino acids, vitamins, oligopeptides, and drugs. And they act as passive facilitator transporters and secondary active transporters, and they're normally categorized into symporters and antiporters. And so SLCs as therapeutics, so basically they have been associated with an increased risk of disease, especially cancer. And now researchers are interested in targeting them as a method of therapeutics to limit the severity of the disease. So discovering new SLC transporters is pivotal in expanding our current knowledge and developing new therapeutics. Like for example, mutations and dysregulations of SLC transporters have been linked to conditions such as cystinuria, which is on mutations on SLC3A1 or 7A9, congenital hypothyroidism on SLC5A5, and other various neurological disorders like epilepsy and autism that are on a mutation on SLC6A8. And so now about folds in SLCs. So SLC members, they contain multiple transmembrane helices, often 10 to 14, and they form distinct folds that define their function. And now with advanced computational methods, as mentioned previously, like AlphaFold, this combined with experimental validation have expanded our knowledge of folds in SLC transporters and they've identified folds like SLC44 and SLC64. And on this next slide here are just some of the folds in SLC transporters. So for the methods in our study, so first we conducted a literature review. And then after that, we gathered relevant information from the PDB database. Mostly, we looked at the EM/X-ray method, release date, the source organisms, and molecular weight, and then, structure, author, publication year, and resolution as well. And so first, we manually collected this data and formatted it, like on Google Sheets using the PDB's custom report option. And then later, after looking at more papers, we expanded our list of SLCs. And then we used web scraping for efficiency. And then so we used our previously collected data that was done manually to validate the data obtained through programming. And then during data collection, we did encounter like issues with duplicate entries of the same structure. So then we just reviewed the literature to identify the correct gene. And so this diagram here is just showing our process, how we did data analysis and then interpretation. And then we went back after expanding our list, um, and then got information on all the new SLCs and the previous ones, and then went back, validated it, and then now we have started to write our paper.
And I'll be talking a little bit about the analysis methods that we used in order to go through our data and make our graphs. And so we used RStudio to make the graphs that we're going to show shortly. We use standard the Dippler package in order to aggregate the data in preparation for the graphs. And we use ggplot2 as well as GraphPad Prism just to make the graphs look presentable. And so I have a few results to share with you guys. You'll notice that there's a question mark on the slide. That's because, as Sahej mentioned, we did run into some issues with the web scraping part of this project. We have currently issues with the EM and X-ray method determination and the resolution associated with the structures, as well as molecular weight. We're still working on trying to get the information accurate. We noticed that there were some inconsistencies with the data that we collected manually, and comparing it to the new data that we got through web scraping. And so if anyone is familiar with web scraping or knows of any resources, that would be greatly appreciated. We have had a couple of students work on the web scraping portion of it. So we do have current documentation of our latest web scraping program, as well as a GitHub link that has all the code. So if anybody's interested in taking a look or helping us out, that would be greatly appreciated. So kind of going through our results, these are kind of the trends that we wanted to highlight. We see that from the PDB database, we looked at 67 unique SLC transporters and 426 unique structures that were deposited in the database. And based on the graph in the slide, we see that the earliest structures were discovered in 1994 and have overall increased throughout time, with a noticeable increase happening in around 2019, with 2020 and 2022 having the highest number of SLC structures discovered. And then this graph just kind of shows the SLC genes by their structure count. So out of the 67 SLC transporters that I mentioned, SLC 3A2, 6A4, and 1A5 had more than 20 structures. And on average, each of the SLC genes had about 6 corresponding structures in the database. And so this graph takes a look at the prokaryotic and eukaryotic source organisms for these structures. Out of the 426 unique structures, an overwhelming 97% of the structures were obtained from eukaryotic source organisms, and about almost 70% of them were from Homo sapiens. Prokaryotic source organisms were first used in 2015 and then followed in 2018, 2019, and 2022, and the most notable prokaryotic source organism being E. coli. And so this is the graph that has the structure determination methodologies. Again, we are unsure if the data that we have is correct, and we would really appreciate some help on the web scraping part of this project just to ensure that we have accurate data. But from what we have so far, the most common structure determination methodology is EM, followed by X-ray, and then some of the few earlier structures were obtained through solution NMR. And so we also are taking a look at the resolution range and structure resolution. And prior to 2016, majority of the structures had a resolution of less than 3. And after 2016, we see a decrease in structure resolution. And after 2016, majority of the structures obtained each year fall under that 3 to 4 resolution range, as seen in the bar graph. And again, this just kind of reiterates that majority of the structures fall under the 3 to 4 resolution range, and they are majority of the time obtained through electron microscopy. And so, like I mentioned, if anybody has any familiarity with web scraping and would be interested in helping our project, this is my email. It's my name, muskaan.sandhu@ucsf.edu, and we would greatly appreciate any help.